Welcome back to our course on Galois theory. We are going to continue on the prime and maximal ideals. In the last class, we talked about the definition of ideals and gave some examples. I'm going to give you some more examples today and some properties. For every ring, there are two obvious ideals. If R is a ring, let R be a ring, any ring, then there are two ideals. One is the trivial ideal. The trivial ideal is an ideal called trivial ideal. Then there is another ideal which is the whole of R. The R itself is another ideal, and this is called improper ideal. This is true for any ring. Now we are going to do so we are going to start with another we are going to define a different kind of ideal. So let's start with a commutative ring. Let R be a commutative ring. Let's take it as with unity. Commutative ring means the multiplication is commutative. Addition is always commutative, but in a general situation, R doesn't need to be commutative on the multiplication. But when you say it is a commutative ring, then the multiplication is commutative. In this case, let's take an element from R. This actually, when you are choosing A, it cannot be 0 and it cannot be the identity of multiplication. Cannot be an identity of addition, it cannot be an identity of multiplication. Then we define an ideal like this. NA is equal to RA, R belongs to R. To give an example here, let's take Z as a integers, and I'm going to take A is equal to 3. So my N3, we will say here it is 3Z. This is my NA is equal to what is going to be 0, 3, 6, 9 minus 3, etc. So my claim is, in general situation, this definitely is an ideal, no doubt. We have already seen this as an example in the previous class. But in a general situation also, this is going to be an ideal. How do you prove that this is an ideal? What is the definition of ideal? The definition of ideal is N is an ideal of R if AN is a subset of N and NB is a subset of N for all A, B in R. That is the definition of an ideal. So what we do is we take an element. These A's and B's are any element from R. Because we already chosen an A here, we'll take another element. So what we'll do is NA of R. So let R1 is an element of R. So what this is going to be R1 RA, R belongs to R. Because R is commutative, we can write this as R1A, R belongs to R. And this is what? This is actually N R1A. And that is actually a subset of NA. Because here, if you multiply this one with anything, that will again become a subset of this. So what we have proved is for any R1, a R1 NA is a subset of NA. So that implies NA is an ideal. NA is an ideal. So we are just taking an element which is different from the identities of addition and multiplication and multiplying that element with every element of R, then we will get an ideal. See, if you take 0, then this will become, this is also another ideal, but that is going to be a trivial ideal. If you take 1, then it will become the whole of R. So we don't want to take any of this. We want to consider a proper ideal. So that's why we are taking something different from 0 and 1. And make sure that this is a commutative ring. This may not be an ideal if it is not commutative. And this particular ideal is called principal ideal. This ideal is called principal ideal. Generated by the element A. Element A. And normally it is going to be denoted by we are going to use this principal ideal in several places. So that's why I thought this is the right place to define that. Okay? We are going to recall one special ring that you already studied when you did the ring theory, the basic definition of ring theory. That's actually ring of polynomials. So we'll start with the ring. Let R be a commutative ring with unity. Then the collection of all polynomials we normally denote by R of x. A0 plus A1x an x to power of n for some integer and all I is coming from R. Finite sum of terms like this. This collection is a ring with the following binary operations. With the usual, I'm not going to write, usual addition and multiplication of polynomials Rx is a ring with unity. Actually a ring commutative ring with a unity with unity. Now we can define principal ideals on this. For example, let me define a very simple principal ideal on the ring of polynomials. It's generated by a polynomial x. So x, this is an ideal generated by x. This is going to be like, this is actually x times p of x such that p of x belongs to R of x. Is an ideal. And what is this ideal? This ideal is the collection of this, actually this ideal is the collection of all non-constant polynomials. The ring of polynomials we are going to use in several situations in the coming lectures. But in the coming lectures, normally instead of a ring, we use field. But even if this R is a field, the R of x is still a commutative ring. R is not a field. So, if R is a field F, still f of x is a ring with the unity. Because we can find out elements in f of x which doesn't have any inverse. So that is the reason, even if you take a field instead of R, the collection of polynomials cannot be a field. Let's start with some properties of ideals. Properties of ideals. Just want to recall a couple of definitions from ring theory. Unit and unity. Unit, an element A in R is a unit if A has a multiplicative inverse. Unity is the multiplicative identity of the ring. Okay? Now, the first property. So let R be a commutative ring with unity. Then let n is subset of R be an ideal. Containing the unity of R. This is a commutative ring with unity, so definitely R has a unity. Then N is an ideal that contains the unity of R. So R is a subset of, N is a subset of R. Now let's take an element from R. That implies R times 1 belongs to N because R is an ideal. So, and 1 belongs to N. So this is an element in N, this is an element in R. So once you multiply these two, it should be an element in N. So this means R belongs to N. So for every R in R, it belongs to N, implies R is a subset of N. Again, N is a subset of R. This implies N equal to R. So this means that in a commutative ring with unity, if an ideal contains the unity of the ring, it is the same as it is the whole ring. So the result is, if N is an ideal of a commutative ring, with unity, containing the unity, then N is equal to R. This is an important result. Next property, again let R be a commutative ring with unity and N is an ideal. In this case, I'm not saying that n contains the unity of R. What I'm saying is, let n contain a unit in R. Unit means that element has a multiplicative inverse. It is not a unity, it is just a unit. Then what happens? So, let U in R be the unit in N, because N has a unit. So this implies U inverse exists. That doesn't need to be in N, but it will be in R anyway. So this implies U times U inverse belongs to N. This is from N, this is from R. So the product has to be in N because N is an ideal. This implies the unity belongs to N because U times U inverse is 1. And in the previous result, if N contains N, then N is equal to R. By previous result. So what is the next property here? If N is an ideal, of a commutative ring, with unity, containing a unit, then N is equal to R. That is another important property of ideal. So let's take a field now. Let F be a field. What is a field? A field is a commutative division ring with unity, which means that the multiplication is commutative, it has got a identity, and every element of the ring has a multiplicative inverse. Now let N be an ideal of F. Okay, and be an ideal of F, and let A belongs to N. This implies A is a unit because A is coming from F and F is a field, so it has to be a unit. It has got a inverse. So this implies that N is equal to F, because if an ideal has a unit, then the ideal is not different from the ring or the field. So the result is a field does not have a proper ideal. A field does not have a proper ideal. It cannot have a proper ideal. We have been using Z for an example of a ring 0, 1, 2, 3, that is a collection of all integers, and ideals are of Z are NZ for some integer n. Here C is a ring, it is not a field. So you can have a proper ideals for Z. But if you consider Q, the set of rational numbers, R, the set of reals, Z, the set of complex numbers, do not have any proper ideals because they all are fields. Every element of Q, R and Z has inverses, multiplicative inverses. Okay? So you cannot have proper ideals for these rings. Now let us recall the definition of ring homomorphism. So let's take two rings here. Let R and R prime be two rings with unity. I'm assuming that is a commutative ring. And we define a homomorphism, ring homomorphism from R to R, R prime. Be a homomorphism actually it is a ring homomorphism if you want to be very specific. Then what happens is let n be an ideal of R. This means that An is a subset of n. So let's take phi of n in R prime. Okay, not in R prime, I will say an image of R prime. Image of R. Consider this situation. We will take an element from here. So let A prime belongs to phi of n and R prime belongs to phi of R. This implies there exists an A in n and R in R such that A prime is equal to phi of A and R prime is equal to phi of R. That is how it is mapped. So we say that, see, let's see, A prime, so what we'll do is A prime times R prime is equal to phi of A times phi of R. This is equal to phi of AR. And this is an element of N. So this actually belongs to phi of N. This is for any element of R prime in phi R. So this implies phi of N is an ideal of phi of R. So the result actually is like this. I'm going to shorten the result. A ring homomorphism preserves ideals between rings. That means if phi is a homomorphism from R to R prime, then if N is an ideal, then phi of N is an ideal of R, then phi of N is an ideal of phi of R. I want to recall one more item from the elementary ring theory, that is canonical homomorphism. So let's assume, let R be a commutative ring with unity. And let N be an ideal of R. So there are actually two rings here. One is R and another one is the factor ring, the quotient ring R over N. So there are two rings. So we can think about homomorphisms. There exists a homomorphism. An obvious homomorphism from R to R over N, defined by phi of A is equal to N plus A or A plus N for all A in R. You can verify this is a homomorphism by going through the properties of a homomorphism. This homomorphism actually, this is a canonical homomorphism from R to R over N. And the kernel of this homomorphism is N. By the way, the definition of kernel of a homomorphism, let's say phi is a homomorphism R to R prime, then the kernel is a subring of R that are mapped to the additive identity of R prime. So here the kernel of this canonical homomorphism is N. We are going to use the canonical homomorphism when we start talking about prime and maximum ideals. I want to touch base with one more concept in ring theory, basic ring theory. It's called field of quotients. This is actually a way of extending an integral domain to a field. So let's start with an integral domain. Let D be an integral domain. So the definition of integral domain is a commutative ring with unity having no zero divisors. That is a definition of an integral domain. So D be an integral domain. It is still not a field, but our aim is to extend D to a field. So there exists, I'm not going to a proof of this because this is an elementary ring theory. So there exists an unique field F which is an extension of D with the following condition. The condition is every element of F can be expressed as a quotient of two elements from D. Actually, this is, again you can say that it's D is embedded in F. If you give an example, Z is a integral domain. It's an integral domain, it's not a field. So how do you embed Z into a field of quotient? Or what is a field of quotients of Z? The field of quotient of Z is Q, because every element of Q can be expressed as a quotient of two elements from Z. For example, 2 by 3 is actually 2, 3 from Z cross Z. So that is the idea of field of quotient.